We have seen what is determinant, how we can define determinant, and how we can evaluate determinant. Now, let us have a look at some application. I will show you two applications. If the determinant is equal to 0, then the rows and the columns in the matrix are linearly dependent. This is easy to show for a 2 by 2 determinant. So consider the matrix 2 by 2 with entries A, B, C, D. And imagine that, say, the rows are linearly dependent. That means either one of them is equal to 0, determinant is then AD minus BC. Say if the first row is 0, then A and B are 0 and the determinant is 0. If the second row is 0, C and D are 0 and the determinant is also 0. If the first column is 0, then A and C are 0 and the determinant is 0. Or if the second column is 0, then B and D are 0 and the determinant is 0. So that means that if the determinant is 0, if they are linearly dependent, not yet. So they are linearly dependent if either one of them is 0 or if one of them is a multiple of the other. So if, say, the first row, let's take the first column, is some multiple of the other column, BD. That means A is alpha B and C is alpha D. With alpha some number. But then the determinant is AD, but A is alpha B minus BC, but C is alpha D. And we have alpha BD minus alpha BD, which is 0. So if the rows or columns are linearly dependent, the determinant is 0. And vice versa, if the determinant is 0, then AD is equal to BC. That means A over B is C over D. That means the ratio of A and B is the same as the ratio of C and D. That means the two columns are in this fixed ratio. That means one of them is a multiple of the other. Another application of determinant is the volume of the body described by the matrix. So consider two vectors, vector E1 with components 1, 0, and consider vector E2 being 0, 1. Now, the matrix A times the first vector is A, B, C, D times 1, 0, which is AC. And the map, or the image of the second vector in this map, ABCD, is the second column of the matrix. So the matrix maps these 2 points, or these 2 vectors, into vectors. The first one has coordinates AC, and the second have coordinates BD. The volume of this square is 1. Well, by volume, we mean the area. In a two-dimensional case, we mean the area. And the volume of this is this one. But if you consider a parallelogram like that, then the volume, or area, is the product of the base times the height. And the area does not change if you shift one side along this line. So if we shift this side along this line so that this point comes to the axis, then it will be easy to find the area. So instead of the vector AC, we want to add some multiple of the vector BD such that the second component is equal to 0. The first component is A plus alpha B, and the second component is C plus alpha D. And we want the second component, C plus alpha D, be 0. That means we want this point to be shifted here, and correspondingly this point shifts down as well. Okay. So, assuming D is not 0, we have alpha is minus C over D. And then this vector will be AC plus alpha BD. So the second component is 0. That was our condition. And the first component is A plus alpha B, which is A, and alpha is minus C over D times B. And then the following rectangle is generated. And the area of this rectangle is the base, which is the first component of this vector, A minus C over dB, times the height, which is D, which is AD minus BC. And this is exactly the determinant of the matrix A. And this shows that the determinant is the volume of the area generated by taking each vector in a unit square and multiplying this vector by the matrix A. Well, actually, if we talk about volume or area, then the volume or area is always positive. So the ratio of the two volumes is positive, and determinant may be negative. Negative determinant means that the matrix A describes a map that converts right-hand side shoe into the left-hand side shoe. Some mirror imaging. So when you take the volume or area strictly positive, then the determinant, the absolute value of the determinant is the ratio of the two volumes. And this remains true even in high-dimensional cases and even for other other areas than a unit square. Special situation occurs when the determinant is equal to 0. An example may be a matrix, say 1, 2, 1, 2. Then if you consider once again these two vectors, E1 and E2, then the first one is mapped to the vector 1, 1, and the other is mapped to the vector 2, 2. And these two vectors also build a parallelogram, but this time with 0 area. So that was, we have seen two applications of the determinant. If the determinant is equal to 0, then the rows of the matrix are linearly dependent, and so are the columns. And the absolute value of the determinant is the volume of the image of the unit square.